Get the recording on. Good afternoon, folks. I'm pleased to be back with you to continue our module going through aspects of handling uncertainty within the context of agent-based modeling. We have already spoken at a basic level about uncertainty induced by stochastics on model outcomes. And last time we did a significant dive into uncertainty, addressing uncertainty through sensitivity analysis with a particular emphasis on parameter sensitivity analysis. Sensitivity analysis that involves systematically altering our assumptions concerning models by varying the values we ascribe to each successive parameter, and sometimes to sets of parameters in turn. Now, we had gone a lot of the way through discussing this issue within our last session, but there were some items that were left to cover, and in our closing couple minutes of the session, I noted my intention to return to some of those issues, just to sort of wrap up that treatment of sensitivity analyses on parameters, or with respect to parameter values. And it is for that purpose today that to that goal that I wanted to return for at least a dozen minutes, perhaps as many as twice that, before going on to initiate our discussion of a set of other methods that fit into this broader rubric of grappling with our uncertainty as we're working with models. So for that purpose, I'm going to call up our slides, and we will jump into particular aspects of uncertainty as it relates to systematically varying our uncertainty, systematically varying our parameter values in a way that allows us to explore many different distinct values for any one parameter, systematically exploring those, while at the same time exploring the values of other parameters in a judicious fashion, a fashion that avoids a combinatorial explosion, while still allowing us to explore the impacts of assuming different particular values with respect to several different parameters. Okay, so I'm going to switch to my slides here and see if I can get them to display properly. Okay. So these are the sort of broad elements we're exploring. We've been hitting on this one and this one. And we will finish up this and then go on to some others. Okay, so people remember that I noted that when it comes to exploring assumptions about parameter values and the impacts of changing our assumptions about those parameter values, the values ascribed to different parameters, I noted that there's a number of ways we could characterize a task there. We could characterize it by whether we're examining one alternative assumptions on the value to be assumed for one parameter in isolation or for multiple parameters at the same time. whether we perform systematic sweeps through parameter values or perform Monte Carlo analysis. As time allows, we may come back to that today. Whether we are varying our assumptions about these parameters only sort of once per particular simulation, we posit that value from then on, or whether we're adjusting our assumptions about that parameter value, say an interest rate or amount of rainfall to be assumed, something about an unemployment rate or the global temperature rise or the temperature rise in our area in a way that varies over time, varies throughout the course of the simulation. And last time we had explored some use of particular models to alter particular parameter values, say one way at a time, and explored the consequence by running the model several times and seeing the degree of variability that was induced in the emergent behavior of the model as measured by some particular outcome. And I noted some of the mechanisms to undertake this within AnyLogic, something we talked further about on Thursday's session and the labs. We also talked about multi-way sensitivity analysis, where we here perform parameter sweeps of more than one parameter, occupying, as it were, a grid of parameter values, successive values on the rows perhaps being considered these, successive values on the columns being considered, I guess I should say, on rows versus columns, these ones here. And we could examine the induced behavior over those. Now, all of this is, a set of options that afford us a chance to examine how uncertainty in a few variables, or perhaps many, impact the results for the simulation. But some of those in listening here will likely have recognized that we're dealing here with a curse of dimensionality. That if we have n distinct parameters, say 3 parameters, and they each vary over C different values, say 10 different values. So we have 3 distinct parameters, parameter A, B, and C in turn. And if each of them has 10 possible values we'd least like to examine, that gives us 10 to the third or 1,000 possible combinations of parameter values to explore. And particularly if we are going to examine on top of that the impact of model stochastics, uncertainty over time in the model, that's actually a very substantive, indeed, amount of computation. And, as the number of possible combinations to examine for each parameter value, and even more so, much more so yet, and the number of parameters we are considering, 3 parameters, 4 parameters, 5 parameters, 6 parameters, it becomes infeasible to exhaustively examine these combinations, very common. So if we went from 3 parameters, each being explored for 10 values, we have 1,000. If we had 6 parameters, each were being explored for 10 values, we'd have 1,000,000. And I noted that there are techniques for reducing this. I noted that dimensional analysis provides us a way of arriving at a very judicious, deeply grounded in understanding of dimensional quantities, ways of reframing a model so that we have fewer parameters to deal with, so we can reduce the number of parameters against which we're seeking to assess uncertainty in model output. from say 6 to 3. And that can very significantly reduce our computational burden. I'm not going to go into that more, but it's a very deep, significant thing, and you will find videos of me holding forth on that for some other classes within the past 10 or so years. A second option is a set of techniques for judiciously selecting combinations of values. And this I wanted to talk about more. This is at once actionable, reasonably common within the modeling literature, and particularly important for agent-based modeling, given the amount of computation that can go into even a medium-sized agent-based model. And the fact that for each specific combination of parameter values we wish to examine, we'll often have to run that model quite a few times, perhaps 10, perhaps more. So the two approaches I want to talk about here go by the name of Latin hypercubes and orthogonal arrays. And in both cases, the idea is to deal with this desire to square this desire at once. I'm using that term in a colloquial sense, not in a mathematical sense, to address at once this desire to examine possible parameters for multiple values, recognizing that we really want to assess model outcomes with respect to parameter A and different combinations of different values for that, and parameter B and different values for that, parameter C and different values for that. We don't want to sacrifice that desire to examine model output for different values of each of those parameters. But at the same time, we want to avoid this explosion in the number of parameters. So we are at once seeking to sail between the Scylla of under-examining how the model behaves with different values. That's one anti-pattern. Or the Charybdis of examining all possible combinations of values, which is typically infeasible. So each of these approaches is a means of judiciously selecting, consciously, intelligently selecting a small set of combinations that will address our desire to examine in some systematic way how the model behaves with respect to different particular values across multiple parameters. Okay. Latin hypercubes will provide strong but a fairly strong but still often quite very readily achievable goal. We're exploring for each parameter P, say parameter A, B, and C, we're guaranteed to explore at least once each of the possible values of A we wish to explore, each of the possible values for B, each of the possible values for C. We'll have at least one examination of any possible of those values we delineated, say each of the 10 values we wish to perform for parameter A, for parameter B, parameter C. But we won't examine all possible combinations together. Just a particular, we'll have that guarantee that any given one of those 10 values for parameter A, we examine at least once. Any of those 10 values for parameter B, we examine at least once. Any 10 values for parameter C, we examine at least once. So if there's some dramatic behavior, some notable behavior that occurs in the model, if we simulate one of those 10 values for parameter A or for parameter B or parameter C. We will see it. We will elicit it. We'll recognize what that value is because we have undertaken it. That's Latin hypercubes. Orthogonal arrays takes that one step stronger. Latin hypercubes provides a strong guarantee. You tell me your combination, your possible values, say the 10 values you want to examine for each of the parameters, and it will explore each one of the values at least once. Not all combinations, but each one of them at least once. Orthogonal arrays goes one step stronger. It tests each pair of parameter values, of possible parameter values, at least once. Not merely providing a guarantee that each parameter has, say, each of the 10 explored, but if you have any pair of parameters, A and B, or A and C, or B and C, we examine actually each specific combination of the 10 possible values for parameter A and 10 possible values for parameter B, or similarly for A and C, etc. Okay, so we're going to talk about orthogonal arrays. Briefly, because I want to get to calibration, which will take us more than one lecture. Okay, so let's talk about Latin squares. Latin squares or Latin hypercubes is a more common term you'll hear in the modeling. There's a set of modeling tools available. You'll find libraries for it in Python or R, etc. Here, for each parameter, I say field, but each parameter, each value of the values we wish to explore, say the 10 values, occurs exactly once. And here we're being intelligent. We're finding combinations of parameter A, what to assume for parameter A, what to assume for parameter B, what to assume for parameter C, that every one of them, those combinations, we're exploring some unique value of one of those. So that when we're done with our set, we have that guarantee. We've explored each of those 10 values for parameter A, each of those 10 values for parameter B, each of those 10 values for parameter C. The idea of Latin squares and how to address it in sampling, I'll just note to perform that systematically and an understanding of the mathematics involved was articulated by British polymath Ronald Fisher of great statistical fame. He was probably the most widely recognized and esteemed statistician in the 20th century. If you go to Cambridge University, you can find a window celebrating his achievements in this because he was an alumnus of Cambridge University, particularly Caius College. And you'll find here, for example, on each row, and each and every one of these rows, yellow occurs once. It occurs in different positions, and never does it occur between all these rows in the same column. Same thing with blue. Blue occurs here successively across different rows, but always in a different column, never in a column that repeats one earlier. Similarly with any other color. And it turns out we can generalize this to develop these Latin hypercube samples. So you can readily in R or Python in any number of different packages, you could ask for a Latin hypercube sampling of, say, 3 different parameters, 10 values each, within some ranges. And it can give you a Latin hypercube that in a parsimonious small set of possible experiments will be guaranteed to hit each of those 10 values for any one of those parameters. Now, if we're dealing with parameters whose values are continuous, what we would do is break that range up over which we wish that parameter to vary overall into, say, 10 different subintervals within that. And you'd seek to draw at least one value from one of those subintervals. They could be at the same size or they could be of different sizes. You could choose accordingly. But any bin that you create, any of those intervals you define for one of those parameters, you can be sure that it's drawn, at least one run has drawn from that, or exactly one run. So this is a way of very cleverly choosing runs of the model for an arbitrary number of different parameters, could be 10 parameters, in a way that is still feasible. It's feasible in terms of the number of combinations. In contrast, if you had 10 values to explore and you needed all combinations of those, every possible combination of parameter A with every possible combination of parameter B with every possible combination of parameter C, you'd have 10 billion, right? 10 to the 10th possible combinations. This avoids that. Latin hypercubes would give a very small set of runs where you could have that number of 10 parameters explored for each of those 10 values. Okay, let's talk about orthogonal arrays. So orthogonal arrays is another technique that has been widely applied in certain experimental contexts. I particularly cite, as I speak to you as a professor of software engineering as well as of modeling, that this technique is used extensively historically within software, where it sometimes goes by the name of pairwise testing or all pairs testing. The key characteristic here draws on some ideas like we saw for Latin hypercubes, but again with a stronger guarantee. With Latin hypercubes, we were guaranteed for each parameter to ensure that any specific value for it, or any specific interval that we delineate, is explored at least once. We're not saying that that value is explored with a particular other interval of any other parameter. No, we just want to assure that we've at least once run the model with a value for this parameter from a certain range, or from, of a certain value. Orthogonal arrays provides a similar guarantee, but for every pair of values. So if we have 10 possible values for parameter A, 10 possible values for parameter B, 10 possible values for parameter C, every combination of A and B of those possible 10 values will be guaranteed to be explored. Not just A in isolation, not just B in isolation, C in isolation, but every 10 of those values for A and 10 of those values for B explored. Every 10 of them for A and 10 of them for C explored. Every 10 of them for B and 10 of them for B and C explored. But not all possible combinations of A, B, and C at the same time. This is very different. So it's a much, much smaller, orders of magnitude smaller number of combinations. And, it exploits the fact that just as you want to be sure that your model is not going to do something loopy, something crazy for any given interval of any one parameter, there's some types of behaviors that it requires two parameters to elicit. Maybe it's a parameter involving contact rate and a parameter involving recovery time, because both of them are needed for it to be, have very large number of infections or very small number of infections. So say basic reproductive number would be very high, very small. So sometimes our concerns are with compatibility, with needing to make sure that two parameters are in the right range to elicit some behavior. So here we avoid the explosion. And this gives some sense here of when we have different parameters. So maybe we have possible case of 3 possible values for 2 parameters, 2 possible values for 2 parameters, and then a final one where just 1 possible value. 100% coverage would require 36 different combinations. You can just do the math. This is 9 times 4, 36. And orthogonal arrays, this sort of reasoning can reduce it to 9. What's more significant is if you have a lot of possible combinations and possible parameters that require that combination. This is 100% coverage. This is the reduced number. And what you can see is judiciously exploring it so that any pair of possible values for each pair of parameters, for a given pair of parameters, is generally within the range that you might contemplate. But if you're considering all possible combinations, it very quickly grows outside the range where you can contemplate it as the number of parameters being considered rise, even with a modest number of bins to explore, intervals to explore for each of them, or possible values to explore in each of them. Okay, so here, I will note that while any logic does not, and I believe this holds for the newest version, have direct support for Latin hypercube sampling or orthogonal array sampling, pairwise sampling. What I have seen people do, and it's a good technique, and I think my group may have done it in the pre-pandemic era, is generate using R, say, a set of combinations for Latin hypercube or for orthogonal array, set of values for different parameters. And then we put that results of the combinations to explore into any logic. And we just look up for each iteration what parameter values to assume for that. So in other words, we do the work. We have R or Python do the work of computing the combinations needed to provide these guarantees, orthogonal array guarantee, pairwise guarantee, or Latin squares. And then we just plug it in and look up what to assume for the next iteration. Very effectively, a very effective way of exploring these things. And provides strong guarantees. It provides guarantees that you're not just overlooking, some range of one parameter that would cause totally different behavior, or of 2 parameters. So these are judicious ways of dealing with combinatorial, of avoiding the intractability of dealing with all possible combinations of values, which, as I say, is generally here impossible. 100% coverage, all combinations is what's shown here. Okay, so we're avoiding that. We're judiciously selecting combinations. Now, I want to return to this issue of another approach, which is the Monte Carlo analysis. I had noted last time I'd even run in front of us in a model Monte Carlo analysis. I drew the value of a parameter from a distribution. You may recall that. I ran the model again and again and again, where the assumptions about a specific parameter were drawn from a truncated normal distribution from this very chair on Friday. what was probably not evident in my abbreviated remarks upon that occasion is that what seems just kind of like potato, potato, tomato, tomato, how do you sample from a parameter? Do you perform a parameter sweep systematically on the one hand versus do you draw its value from parameters that might have seemed from my remarks a somewhat arbitrary choice, flavor of the day, choose what technique you will. You could be forgiven for thinking that from my brief remarks, but you would be wrong. It turns out there's an enormous difference between the two. And this difference becomes much greater when we are dealing with large numbers of parameters. When we're dealing, folks, with this curse of dimensionality, the fact that the number of possible combinations of n parameters rises as c to the n. Let's talk about this. I can't afford to spend the balance of the lecture on this, because I do want to get to calibration, but I'll make some brief remarks. If we consider n different parameters, we consider going from 1 parameter to 2 to 3 to 4. As I allude to here, there's a curse of dimensionality. Monte Carlo analysis. So the techniques we were talking about last time, and I'm tempted to show them just to make this more concrete right here, where we examined systematically in parameter sweeps what's shown here is 2 parameters, one going from 5 to 25 with a step size of 5. So 5, 10, 15, 20, 25. The other with infection probability from what looks to be 0 to 1 with a step size of 0.1. We're examining all possible combinations of these. That doesn't scale as the number of different parameters we consider goes up from 2 to 3 to 4 to 5. It blows up in this curse of dimensionality, blows up geometrically, or you could be forgiven for saying exponentially. Instead, Monte Carlo approaches take a different tack. They draw parameters from distribution, the value to assume for parameters from distribution. And the model is run, this is performed many times, each with different assumptions about parameters. Or, as I have noted, that often you will, for each assumption about those parameters, you will run the model itself many times. You'll have an ensemble of realizations. Maybe you'll run the model 10 times for each parameter value you draw from the random distribution. What emerges as outcomes for the models. And that was kind of the idea that I meant to give on Friday. But what I didn't talk about is the implications for sampling. And this is really important. And here's the kicker. For a given amount of computational effort, if you can only run the model so many times for different parameter values, generally you will get far bigger bang for the buck, far more out, far better sampling from Monte Carlo draws than you will by sampling the grid of possible values of combinations of parameters. Parameter A, all its combinations. Parameter B, all its combinations. That forms a grid, right? columns could be parameter A, the rows could be parameter B. Here, as the number of dimensions go up from 2 parameters to 3 to 4 to 5, that's capital D, the number of combinations goes up. The effort scaling, by contrast with Monte Carlo scales, it rises with the number of samples we draw. It doesn't go up geometrically with the number of parameters, distinct parameters. No, each value we draw is for all of those N or D, capital D parameters. This is capital D parameters. So each of these N combinations of each of these N Monte Carlo samples from D parameters. And it turns out that we sample it much more effectively. So of course, a grid will spend a lot of time commonly in areas of the space of possible values that are low probability in terms of what we assess their likelihood of occurring. Commonly, we have some sort of prior distribution over these parameter values, perhaps joint, perhaps individually. But with a grid, we'll spend a lot of time on the periphery, on the areas that are unlikely. In Monte Carlo, we tend to concentrate our samples in very probable regions. We perform our sampling where it is plausible that we have values, and we use our limited amount of effort that we have computationally to much greater effect with this sampling. It's an unassuming thing. You might think, again, what's the difference between sweeping? Well, it's actually a big difference. And as the number of parameters you want to examine goes up, as it's just going to be vastly more favorable to draw them from a distribution, where if we're drawing n different values, if we want to examine n different combinations of parameter values, parameter vectors, as it were, to examine, we can do so directly rather than spending huge amounts of time exploring this d-dimensional grid where we spend much of our time in areas far from our point of focal concern. So the fact that I last time showed running this model with different assumptions about these parameters drawn from a distribution was no accident. It wasn't just a side note or curiosity of, look, this is what you can do. This actually lets you sample far more effectively as the number of parameters you're exploring goes up. It becomes overwhelmingly more desirable than the very coarse grid you can afford to explore with capital D, different parameters. Okay. Let's see, a few other closing comments here. First of all, one thing I've been concentrating on in this discussion, last time in this, is parameter-based sensitivity analysis. But a close cousin of that, and one that's oft handled with parameters, is the initial state of the model. What's its initial state? Frequently, we don't have the luxury of knowing exactly the initial state. If we have some inkling of it, if we have some data, it's often incomplete. It's only approximate. It may be with some summary measures. So a useful type of sensitivity analysis for many models is to vary the initial state. So like run the model from different assumptions about the initial state. And in agent-based models, if you think about it, the set of possible states that the system could be in, if you hark back to our discussions in this course, not 6 weeks thence, where I spoke about state space and its dimensionality. The size, the mathematical size of the possible set of possible states is astronomical. If we have, I don't want to confuse you with n from earlier. So if I say I have m agents and each of them can be in c possible, so I'll call it s possible states, then we have s, that's the number of states, to the power m possible states. So each person, say each agent could be in can be in s possible states, and therefore, if we have one person, they can be in s states. If we have two people, it can be s times s possible combinations of states with 3 s times s times s, and so on, s to the m, the number of people. Here we generally can't exhaustively sample, certainly, and only approximately sample from these initial states. So we often will sample from it in a way that tries to keep constants, try to match some overall statistics we might know, or some overall features we might know of the situation. Another way we can approach it, which is extraordinarily common, is through a technique known as variously as equilibration, or burn-in. Here we take the model. We may give a gesture at some initial state, but we run the model for some period of time that's a burn-in period until it kind of adjusts to an imbalance situation. It reflects the fact that our initial estimate of model state was probably off in some way. And by running the model for, say, 5 years or for 10 years, it may get into a state where really its dynamics are properly dictated by what we posit for how agents update, etc. And after that, then we're playing for keeps. Then we run it forward and seek to understand how different policies would affect it. So we have what's called the burn-in period, which goes for some initial period of time just to get the model in balance. Because often our initial guess at initial state is out of kilter with what we assume about how agents update, and we just can't easily recognize it. It's not obvious from our description of how agents update that it's incompatible with what we assume for the initial state, that it will lead to transience, it will lead to disequilibria, it'll lead to swings early on in the first year or two or what have you that are unrealistic in the world, that are not empirically grounded. And for this reason, we often run a model for some burn-in period. Right. I noted these impacts on policies last time. I will finally just remark here, and it's possible that I will leave it here for today, that when we are building an agent-based model, just like any dynamic model, I have argued that structure determines behavior. It's the form of the model. And when I say the form of the model, we're talking, for example, stages of a natural history of infection. That state chart we've seen many times, SIR versus SIRS. Or it could be how we represent states associated with care-seeking attitudes towards care-seeking, the possible states, the possible combinations among them. Or it could be states with regards to someone's being in relationships and the healthiness of those states, the healthiness of those relationship states, whether it's toxic, whether it's abusive, whether it's individuals have separated, etc. Our structure in the model, in the form of, say, state charts, but also in terms of what messages are set from one agent to another, how does the surrounding environment influence someone, the possible mechanisms by which I evolve, by which agents interact bidirectionally with their environment. It's those aspects of structure, more so than any one parameter value, that often foundationally shapes what behaviors are possible. It's not that parameters don't make a difference. It's just they tweak what's possible. They tweak system behavior within the range that's made possible by the structure of the system. If you don't have, in an SIR type context of infection transmission model, if you don't have loss of immunity, you're not going to get the ability for susceptibles to rise again. If in a classic SIR with no incoming, no bursts and no in migration. If you have a certain model structure with just susceptibles infected and recovered, and no loss of immunity, and no latent period, you're not going to get oscillations. You get oscillations, you get the ability for susceptibles to be replenished, etc., for infection to stay circulating with certain model structure. So structure is often the defining thing that dictates possible behaviors. And so it behooves us to think explicitly and deeply about how the structural assumptions of our model, which are assumptions just as much, I tell you, as those about parameter values, it behooves us to consider how do those structural assumptions shape model outcomes, and how does varying those structural assumptions in some way change model outcomes. How does the assumption that there are asymptomatic individuals as well as fully symptomatic individuals affect things? How does it affect things to posit that there are some individuals who are much more infectious than others? How does it affect things if we posit that some individuals may acquire the infection more than once? How does it change the situation if we posit that some individuals pass away more quickly because of the infection than wouldn't otherwise? If we change our structure in our model, if we change it so that infection is not just passed person to person, say via aerosols or droplets, but say not just with droplets, but say with aerosols that remain in a space after the transmitting individual has left. After the person who is infectious has left, they remain in the space as a kind of cloud of possible infections. Or, by contrast, if we wish to look at the effects of how model outcomes differ, if we posit that it's not just spread person to person, so with droplets or with aerosols, but via surfaces, how does that impact output? Here we're changing mechanism. We're changing the structure of the model. And we will often see very notable changes in model behavior that are instructive, that help educate us as to how our structural assumptions on the one hand affect model outcomes on the other. Changing those structural assumptions will sometimes induce changes in which interventions look more desirable than others. The effects of contact tracing may be very, very different if we have asymptomatic individuals, for example. The effect of introducing vaccination may look very different if individuals can acquire the infection more than once without it. If we posit that someone's immune system is boosted by exposure to pathogen, that may have a very material impact on how that pathogen stays resident in the population. So, model uncertainty is one of the most profound sorts of uncertainty we can consider, and the most important ones when thinking about a model. I will further note that some amounts of model uncertainty can be addressed, not always, but there are times where some amounts of model uncertainty can be addressed by parameter variation. And if I had my druthers, if I had my presence of mind, I might have called up in front of you any logic at this point and opened a judiciously chosen model. I can't promise for you that, but I will open a model that might be illustrative of the point that I'm about to make. In fact, perhaps this very one that that stands before us now. If we were to assume, for example, within this very model, and I will double click on this and zoom in a bit so you can focus on the salient state chart. If we were to wish to alter this, we could do so in a number of ways. One way, we could have this resulting transition. We could, for example, add another transition here, which reflects natural recovery, where the rate of that natural recovery, the hazard rate, is given by a parameter. And turning that parameter to a value of 0 would disable natural recovery, leave the only type of recovery to be this treatment-mediated recovery that stands before us here. Alternatively, we could turn on that natural recovery in a way that would allow us to examine if virtually all infection were natural in character. Another thing we could do is, for example, make this transition, and I will zoom out here. Okay, that isn't what I meant to do. Thank you. What I wanted to do was to, yes, I know. Here, we could set a guard given by a parameter value and enable and disable this treatment effect on infection, depending on that, if that parameter was true or false. And if I could just further this point a little bit more, if I could go to, and again, okay, this is, it's already open. Well, I see. So it's this lower one. Forgive me. Here we have another model. This is one we've also seen together. And here you'll notice that the rate of this transition is given by 1 divided by the mean immunity duration. We could, for example, set the mean immunity duration to an exceptionally large value, essentially setting it to infinity to disable this transition. Alternatively, we could frame the transition as in terms of being the rate of it being given by a hazard rate and set that hazard rate to 0 instead of 1 over a mean time. Similarly, if we wanted to structurally disable spread of infection at all, we could set this, yes, I know, this rate here, the hourly contact rate to 0, or set the rate of recovery. If we wanted infection to be permanent, we could set the rate of recovery, the mean recovery time to essentially infinity to disable this progression. We are effectively altering, we're sort of giving the appearance of altering the effect of altering the structure here by altering parameter values to extreme values. And through those techniques, you can often gain great insight. So when we spoke from this chair on Friday about extreme value testing, one of the many reasons that it enjoys virtues to recommend it is the fact that we can essentially achieve a form of structural sensitivity analysis in many cases, effects that in essence mimic disabling and enabling areas of the model so that you can better understand drivers for model outcomes and the impact of structural assumptions of a model on those outcomes through this proxy of changing parameter values. There are other ways. If we wanted to add asymptomatic infectives, we could literally add a state here, have infection come in, have a certain fraction go to that asymptomatic state, a certain fraction go to this symptomatic state, and have both of them recover. If you wanted to add a state of some sort of super spreader, you could do that as well and have that other person, that other individual, have a higher rate of contact. If you wanted to have a latent state, a state of latent infection, you could add a state exposed or latent, whereby prior to becoming infective, there would be a state here, and you could examine the impact of that on model outcomes. So, in short, when it comes to examining the degree to which the behaviors of our model are contingent upon our particular assumptions about parameters, assumptions about structure, we do well to systematically examine alternative assumptions. And parameters provide us, both for structure, but especially for altering explicitly and repeatedly our parameter values, more effective ways of doing this. They have their limits, they have their scaling limits, their tractability limits, because of the curse of dimensionality that besets us when we wish to examine model behavior when varying large numbers of parameters through judicious choice of judicious methods, be they Monte Carlo approaches, be they use of Latin squares or Latin hypercubes. Yes, I know. Or or orthogonal arrays, we can combat and oft defeat that curse of dimensionality and secure a better understanding of whence model behavior arises, what drives it, and how said model behavior and indeed the impacts of interventions of interest are shaped by those assumptions. Next time, on Wednesday, we will gather to examine an additional element of model uncertainty and how a different technique, also involving altering assumptions about parameters, can seek to address data gaps, can seek to better exploit data gradients, where we have data not about any one parameter value often, but about emergent model behavior as a whole. And that will bring us, dear viewers, to the cusp, to the point of talking about calibration and talking more generally about systems data science for all its contemporary parts. And with those words, I will close this session. I will retreat to my office and reopen it at the same channel for those who would like to dialogue. Thank you.